Somewhere beyond the light, there are places where physics itself folds, where time has no direction and gravity hides more than it reveals. Black holes, once imagined as the universe's tombs, might instead be its secret passageways. Every photon that vanishes at their edge could be the beginning of something else, in a place we cannot see yet. What if every collapse is a creation in disguise? Tonight, we dive into that question, not with answers carved in certainty, but with the quiet promise that beyond every horizon, something is still happening, something waiting to be found. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you can tell me where in the world you are watching from and what time it is, I would love to read it in the comments. 1. Could a black hole be less a destroyer and more a gateway? For a century, black holes have been the monsters of astrophysics, objects so dense that not even light can escape their pull. But the mathematics that describe them, when pushed to their limits, refuse to end neatly at destruction. The equations of general relativity continue beyond the event horizon as though something else should exist there. If the singularity were not an endpoint but a threshold, then perhaps a black hole does not close the story of matter and energy but sends it onward in another form, into another realm. The idea of a gateway redefines gravity from executioner to transporter. Space itself curves so severely that it folds, and in that fold could lie a path that bypasses our visible universe entirely. Such a passage might not even require exotic new physics, just an extension of Einstein's geometry beyond our current reach. For an external observer, the object seems to vanish forever. Yet for whatever crosses the horizon, the story might continue along a hidden dimension of the same cosmic fabric. Physicists have explored this mathematically through what are called Einstein-Rosen bridges, solutions that link two regions of space-time. Though unstable in our current models, their existence in theory suggests that the universe permits connections beyond our sensory world. A bridge like that would not break causality, but expand it, creating a layered cosmos where death and passage are relative to perspective. What ends for us could continue elsewhere, unseen yet consistent with the same physical laws. If such gateways exist even fleetingly, their influence could ripple through cosmic history. The strange jets that shoot from galactic centers, the perfectly balanced spin of some black holes, the subtle structure of gravitational waves, all could be shadows cast by processes occurring beyond our horizon. A black hole as a gateway would mean the universe is less about finality and more about transformation, an idea both terrifying and liberating. 2. What if falling into a black hole means not death, but transition? To most physicists, the phrase falling into a black hole evokes annihilation by tidal forces so extreme that they stretch atoms into threads. Yet relativity tells us that for the falling traveler, crossing the event horizon is unremarkable. Nothing special happens at that precise boundary. What happens next depends on the true nature of the singularity. If the core is not infinite density but a doorway into another space-time region, then the fall becomes a migration, not a termination. This transition would change our understanding of continuity. Instead of being shredded, information might flow through a tunnel of curved space-time and emerge reorganized elsewhere. The equations allow such a route under certain energy conditions, and quantum corrections could make it possible in brief pulses. The traveler would not witness fire or chaos, but the stretching of coordinates, the slowing of outside time, and then an inversion where inside becomes beyond. From the external universe, that person or particle would seem frozen at the horizon forever. To the traveler, however, the journey would complete in finite time, reality would bifurcate. One version still visible, slowly fading, and another continuing past a point that no external observer can describe. In this sense, black holes could be natural laboratories where relativity and quantum mechanics test the limits of what death means for matter. If transition is the right word, it suggests that the universe itself is dynamic at a scale beyond visibility. Nothing is truly lost, only relocated in ways that our tools cannot yet map. What appears as cosmic death could actually be the dispersal of existence into new coordinates, proving that the end of space for one observer is the beginning of time for another. 3. Do Einstein's equations secretly describe bridges rather than voids? Einstein's field equations balance spacetime curvature with energy and momentum, a conversation between geometry and matter. When applied to massive collapses, they yield black holes, but their symmetry allows mirror solutions where spacetime folds back on itself to connect two regions. These theoretical bridges appear not as empty gaps but as continuous surfaces, implying that gravity's ultimate expression is not collapse but linkage. A bridge interpretation replaces the image of spacetime torn apart with one of spacetime woven together in unseen ways. The equations themselves remain agnostic. They do not forbid such connections, only require that certain conditions be met for stability. If nature occasionally satisfies those conditions, even for a moment, then the universe may already contain countless hidden bridges blinking in and out of existence at quantum scales. The implications reach far beyond astrophysics. A bridge solution hints that the universe values connection over isolation, that every point of gravity could hold a potential route to elsewhere. What we perceive as infinite density might just be the mathematical simplification of a folded geometry too compact to visualize. Einstein's mathematics, once read as a warning of collapse, might instead whisper of pathways through the cosmos that bypass the limitations of light and distance. In that light, black holes become not cosmic graves, but the structural knots of space-time. They keep the universe coherent, tying regions together across unfathomable scales. The challenge for physics is to translate this hidden grammar of connection into observable effects, echoes in gravitational waves, distortions in background radiation, or patterns that suggest geometry looping upon itself like a secret sentence written in the dark. 4. Inside the singularity, does space truly end or begin again somewhere else? The singularity is the point where mathematics fails, where curvature and density go to infinity. Yet infinities in physics are usually signs that the theory is incomplete, not that nature is. Many researchers suspect that deep inside a black hole, quantum gravity replaces the singular point with a finite region of extreme but calculable density. If so, the interior could curve back outward, forming the embryo of a new space-time domain. Such a beginning would make every end a rebirth. When space folds so tightly that distances collapse to zero, the geometry could reinflate on the opposite side of the fold. The laws governing that inflation might resemble the physics of the early Big Bang, suggesting that black holes and cosmic creation are phases of the same underlying cycle. The boundary of one reality becomes the seed of another. If this is correct, singularities are not defects, but engines of renewal. They transform exhausted matter and energy into the initial conditions of a fresh cosmos. Observationally, we cannot see beyond the horizon, but the population of black holes throughout galaxies could represent an ongoing cosmic production line, each singularity brewing its own universe in a higher dimension beyond our reach. This view reconciles creation and collapse as two motions of one process, Instead of asking where space ends, we might ask how often it begins. The singularity becomes not a wall, but a mirror reflecting existence into new forms, ensuring that the universe never runs out of places to unfold. 5. When matter disappears into a black hole, could it reappear in another universe? Conservation of information is one of physics' sacred principles, yet black holes challenge it by hiding everything behind a horizon. Hawking's discovery that black holes radiate gradually complicates the picture. The radiation appears random, but perhaps it encodes information in a form we do not yet understand. If that information resurfaces elsewhere, it might not return to our universe at all. It could emerge in a sister realm connected through the black hole's core. This possibility extends quantum mechanics into the grandest of scales. Entanglement could link the interior of a black hole with regions far beyond our cosmic boundary, allowing data to migrate through a higher dimensional corridor. From our side, the disappearance looks absolute. From the larger system's view, it is merely transfer. The universe thus conserves not objects, but meaning, relocating it beyond the limits of our observation. Such a mechanism could explain why our universe began with ordered conditions instead of chaos. The information that defines its structure might be heritage from a previous cosmos whose matter collapsed into black holes. The radiation we detect as background noise could be the faint echo of that ancestral memory, streaming from gateways that closed billions of years ago. If so, every atom around us might carry a trace of another universe's history, rewritten through gravitational collapse and rebirth. What vanishes into darkness here could be the dawn elsewhere, making every disappearance a hidden creation. 6. Could every black hole in our universe be the birth cry of another cosmos? The symmetry between black holes and the Big Bang has long intrigued theorists. Both involve immense density, expanding or contracting space-time, and horizons beyond which we cannot see. If a black hole's interior inflates instead of collapsing absolutely, it could form a separate, awanding universe disconnected from ours, except through that initial bridge. From within, its inhabitants would perceive a normal cosmos with no awareness of the parent universe outside. This concept, known as cosmic reproduction, suggests that universes breed through gravitational collapse. The constants of nature in each offspring might differ slightly, depending on the conditions of the parent black hole. Over countless generations, universes that produce more black holes become more common, a kind of cosmological natural selection operating across the multiverse. Our own universe, abundant in black holes, might be a successful parent. If true, black holes are not cosmic waste bins, but wombs of creation. Their singularities are contractions that give birth rather than destroy. The explosive expansion we call the Big Bang could simply be the inside view of one such birth, the silent echo of a black hole from an earlier universe opening into ours. The cycle of death and creation becomes an unbroken lineage written in the language of gravity. This idea changes how we see existence. Instead of one universe with many black holes, there could be an infinite family tree of universes connected by them. Each collapse is a cry of labor, each explosion a first breath, and every dark horizon hides a genesis we can never witness. 7. If there is an exit, where is the entrance? A tunnel implies two mouths, yet we observe only one. If matter can leave our universe through black holes, symmetry demands that somewhere else, perhaps in another domain, it must enter. The absence of visible entrances may mean they lie beyond our observable horizon or within dimensions folded outside ordinary space. Their invisibility may be the very reason the multiverse remains hidden. Searching for an entrance requires rethinking direction itself. In higher dimensional geometry, inside and outside are relative. What we call an exit could appear as an inflow to an observer on the other side. To them, our universe's gravitational wells might look like fountains of creation, pouring energy outward. The duality between exit and entrance dissolves once space becomes multidimensional. Some researchers speculate that phenomena like gamma-ray bursts or sudden high-energy outflows from distant regions could be glimpses of such entrances in action. The data are inconclusive, yet the symmetry of nature makes the question unavoidable. Energy rarely disappears without a counterpart, and the cosmic ledger must balance somewhere beyond our sight. If entrances exist, then the universe is not a closed chamber but a vast interchange of realities. Every black hole we observe could be one half of a larger architecture, whose other half we may never reach, but whose presence might shape our universe's evolution in ways we are only beginning to imagine. 8. Are wormholes simply the visible faces of hidden black holes? Wormholes have long been treated as separate theoretical entities, but their mathematics overlap heavily with black holes. Both arise from solutions to Einstein's equations, involving extreme curvature. A wormhole is essentially a bridge with two horizons instead of one. Some physicists suggest that a rotating or charged black hole could naturally evolve into a wormhole if its interior avoids singular collapse through quantum effects. This interpretation would mean that black holes and wormholes are not different species, but different life stages of the same object. Under certain conditions, a black hole might stabilize into a traversable structure for a short time before collapsing again. Such transient openings could be microscopic or vast, connecting distant parts of the cosmos or even parallel universes. Their fleeting nature would explain why we detect no stable wormholes, yet still sense anomalies in gravitational data. Observationally, if a black hole acted as a wormhole mouth, its radiation and accretion behavior could show deviations from classical predictions. Slight irregularities in timing, jet alignment, or polarization pattern might hint at geometry more complex than a simple sink. Detecting these would require instruments capable of measuring gravitational lensing at unprecedented precision, a challenge within reach of the next generation of telescopes. If proven, the wormhole interpretation would unify two of science's most captivating ideas under one reality. The terrifying collapse of matter and the elegant shortcut through space would turn out to be the same phenomenon seen from opposite sides, a reminder that in the universe, destruction and passage may share a single doorway. 9. Beyond the event horizon, does time flow differently to create a new reality? Einstein taught that gravity slows time. Near a black hole, this effect becomes extreme. To an outside observer, time for an infalling object nearly stops at the horizon. But inside, the roles of space and time switch. The direction towards the singularity becomes as inevitable as the forward flow of time in our world. This inversion could create a distinct temporal domain, effectively a new version of reality governed by its own chronology. Such a realm would have its own arrow of time and causal structure. To any observer within it, events would proceed normally, yet from our frame, those same events might unfold over an eternity. The boundary between the two becomes not a wall but a clock face, whose hands move at incompatible speeds. The relativity of time becomes so complete that one universe's moment could be another's infinity. Quantum theory complicates this picture further. At microscopic scales, fluctuations of spacetime could cause localized reversals or loops in temporal flow. Inside the horizon, These fluctuations might accumulate, weaving a new timeline disconnected from ours. The singularity then is not only spatially separate, but temporally autonomous, birthing a region with its own history. If time can indeed restart or reshape itself within a black hole, then the term new reality is literal. Each collapse would carve an independent chronology into the larger cosmos. Our universe, too, may once have been a moment of reborn time inside the horizon of something much older. 10. Could the Big Bang itself be the other side of a massive black hole? The conditions at the beginning of our universe mirror those inside a black hole. Immense density, curved spacetime, a rapid outward expansion bounded by a horizon. This resemblance has led some physicists to propose that the Big Bang was not a singular beginning, but the emergence of a new region from within a collapsing star or cosmos. The black hole from another universe could have given birth to ours, its interior expansion appearing to us as a Big Bang. In this model, the parent universe undergoes gravitational collapse, while the offspring universe expands within the internal geometry created by that collapse. The event horizon acts as the boundary between generations of reality. From the outside, energy falls inward. From the inside, space inflates outward. No contradiction exists because each side measures its own time and direction independently. This perspective explains why our universe seems finely tuned. The physical constants we observe might be inherited from conditions inside the parent black hole, subtly altered by quantum effects at the bridge. Over countless cycles, only universes that allow black holes, and thus offspring, would proliferate, creating an evolutionary pattern across the multiverse. In this sense, the Big Bang was not an explosion from nothing but a continuation from something older and deeper. If our cosmos truly began inside a black hole, then every telescope that peers into deep space is looking into a memory of that passage. The background radiation would not only be the afterglow of creation, but the faint echo of a boundary crossed, the silent reminder that beginnings and endings in the universe are never separate. They are two sides of the same horizon. 11. Does each galaxy's central black hole connect to a cosmic twin elsewhere? Supermassive black holes sit at the heart of most galaxies, and their masses scale with the stellar bulge in a relation that suggests deep coordination rather than coincidence. One speculative reading is that this coordination reflects a hidden coupling to partners outside our universe, with each central engine mirrored by a twin beyond our horizon. If galactic evolution is influenced by exchanges that we cannot see, the tight correlations in mass and spin would be the visible residue of an invisible handshake. The galactic center becomes not only a gravitational anchor, but a possible junction to structures that do not share our sky. Feedback from these central engines sculpts the fate of gas, stars, and dust across hundreds of thousands of light years. Jets collimate with exquisite precision and maintain coherence across astonishing distances, hinting at boundary conditions that are unexpectedly stable. A twin connection could impose those boundary conditions from outside our space-time, as if the jet is guided by alignment rules that extend through a bridge. The galaxy we observe would then be half of a wider dynamical system whose full geometry remains hidden. Gravitational waves from mergers near galactic centers might encode faint signatures of this partnership. Deviations in phase evolution or polarization could betray interactions with degrees of freedom not accounted for by ordinary four-dimensional space-time. Even non-detections can constrain such ideas by showing how closely our observations match general relativity, tightening the room where hidden twins might act. Each new detection becomes a test of whether the center is alone or coupled. If a twin exists, symmetry would demand influence in both directions. Star formation cycles, bar instabilities, and quasar lifetimes could be synchronized across domains that do not share light. The cosmos would be a larger organism whose organs are galactic hearts beating in coordinated rhythm, and our measurements would be the stethoscope pressed to one side of that body. 12. Could information swallowed by a black hole still exist, just not here? The black hole information problem pits quantum unitarity against classical horizons that hide everything behind a perfect curtain. Many modern approaches argue that information is never destroyed, and that what seems lost is redistributed in forms we cannot yet decode. Hawking radiation may carry subtle correlations that look thermal only at first glance, preserving the book while shredding the pages. In this view, the information still exists, but the library has moved. One possibility is that information becomes encoded on the event horizon as microscopic degrees of freedom, whose structure scales with area rather than volume. The holographic picture treats the horizon as a data surface from which the lost story can, in principle, be reconstructed. The difficulty is practical rather than fundamental because extracting that story may require precision beyond any realistic experiment. The universe respects its accounting even if it hides the ledger. Another option is that information exits through channels that are not part of our space-time, slipping across a bridge where our instruments cannot follow. From the global point of view, the wave function evolves smoothly, while from our local frame the record appears erased. The mismatch between frames becomes the illusion of loss. What is absent to us is present elsewhere with perfect fidelity. If this is correct, the question of where the information is kept is less important than how it remains consistent. The answer would bind gravity and quantum theory into one narrative, showing that reality is not a set of separate rooms, but a single house with hidden passages. Our measurements explore the hallways we can see, while the rest of the house holds rooms that keep the story intact. 13 are white holes, the mirror images of black holes. A white hole is a hypothetical object that nothing can enter and from which matter can only emerge. It is the time reverse of a black hole, a concept born straight from the symmetries of the equations. If black holes are cosmic sinks, white holes would be cosmic fountains. The mirror idea tempts us because nature often prefers paired structures when equations allow them. Astrophysics has never confirmed a white hole, and for good reason. Any realistic environment would shower it with matter and radiation, yet by definition it cannot absorb a thing, so stability looks impossible. Quantum effects could change this story if white holes appear as brief end states during evaporation or as transient outlets of bridges. In that picture, the fountain sprays only for an instant, measured in the right frame. Some short energetic transients in the sky have been interpreted as wild candidates for such outflows. Fast radio bursts and peculiar gamma events push imagination toward exotic engines, although conventional models remain strong. The white hole idea survives on the edge of what the data permit, waiting for an unmistakable signature like a spectrum or polarization pattern that cannot be faked by known processes. Until then, it serves as a conceptual tool to test how faithfully time reversal can be realized in nature. If white holes exist even fleetingly, they would close a loop. Black holes would write matter inward, white holes would write it outward, and bridges would be the grammar connecting the two sentences. The cosmos would speak in paired clauses, where every sync implies a source in a language we are only beginning to read. 14. Could quantum entanglement reconnect what gravity tears apart? Entanglement links particles so that measurements on one correlate with measurements on another no matter the distance. Gravity, by contrast, separates worlds by curving space and trapping information behind horizons. The suggestion that entanglement could stitch spacetime back together replaces competition with collaboration. Where geometry disconnects, quantum bonds reconnect. Some researchers propose that the very fabric of spacetime may be woven from entanglement itself. In this view, the strength of connections between quantum states determines the strength of geometry, like threads determining the tightness of a cloth. A wormhole could then be the geometric manifestation of a pattern of entanglement, not a tunnel carved through stone, but a seam sewn by correlations. The bridge becomes the shadow of information sharing. Black holes fit naturally in this story. The entanglement between interior and exterior modes near the horizon may set the rules for radiation and evaporation, and the puzzle of information becomes a question about how those correlations evolve. If entanglement truly builds geometry, then changing the pattern could open or close routes that matter can follow. The map of space would be a map of relationships rather than distances. This perspective invites experiments that look for how quantum correlations influence gravitational signatures. Tabletop tests with massive superpositions, precision interferometry, and studies of gravitational decoherence all search for the boundary where quantum links begin to tug on space-time. A positive result would mean that reconnection is not only a metaphor but a mechanism showing that the deepest repairs in the universe are done with threads we cannot see. 15. Was our universe born inside the black hole of another universe? The initial conditions of our cosmos are remarkably smooth and uniform, despite quantum jitters that should have made a mess. Cosmic inflation explains much of this, yet a complementary story is that our entire observable region emerged from a parent black hole whose interior geometry inflated into a new cosmos. The inside view of that inflation would look exactly like a hot, dense beginning. The outside view would look like matter falling across a horizon. If this lineage is real, then some of our constants and symmetries may be inherited traits. Slight differences in the parent collapse could seed slight differences in the offspring laws, creating a family resemblance across generations of universes. Over enormous numbers of births, the traits that favor black hole production would dominate, since only those lineages reproduce. Cosmology becomes a tree rather than a single trunk. Evidence for such ancestry would be indirect, appearing as telltale patterns in the cosmic microwave background or in the statistics of black hole masses across cosmic time. A subtle correlation could hint at rules written before our Big Bang. Even if the data remain neutral, the hypothesis serves as a bridge between two extremes of physics, showing how collapse and creation might be the same engine seen from opposite seats. To live inside a descendant universe is to accept that our horizon is a generational boundary. We cannot visit the parent, but we can study our own traits and infer a past we will never observe. The sky then becomes a genealogical record, and every black hole we find is a reminder that the family continues. 16. Do black holes recycle cosmic matter into new universes endlessly? Recycling suggests a loop where outputs feed new inputs in a cycle that never ends. In gravitational terms, what falls inward could seed conditions that blossom outward somewhere else. Each generation enriches the next by processing matter under pressures that forge structure from chaos. Stars die to feed black holes, and black holes may give rise to new stars in new realms. Such a loop could provide a natural answer to why the cosmos does not run down into uniform emptiness. Dissipation in one region is resurrection in another, with entropy exported across boundaries that renew it as order. The second law remains safe when viewed globally, while locally, pockets of freshness keep emerging. The multiverse becomes a thermodynamic engine that never loses its spark. On the observational side, the demographics of black holes across epochs act like a census of potential births. Their formation rates, spin distributions, and environments tally the resources available to the next generation of universes in the cycle. If the loop favors certain mass ranges, we should see those ranges emerge repeatedly, as if the cosmos remembers what works best. The numbers on our side of the ledger could foreshadow activity beyond our sight. Endless recycling paints a picture both austere and generous. Nothing is wasted because nothing is allowed to rest forever. The universe keeps reinventing itself by sending its exhausted parts through crucibles that return them renewed, and black holes sit at the heart of that renewal. 17. When two black holes collide, do two universes merge as well? Mergers produce some of the most violent events in nature, ringing spacetime with gravitational waves that cross billions of light years. If each black hole links to a separate region beyond our universe, a collision here would correspond to a junction there. Two bridges would fuse, and their far ends might be forced into a new configuration that blends histories. The idea is speculative, yet irresistible, because it treats the multiverse as a connected network rather than separate islands. The gravitational wave signal might carry faint fingerprints of this deeper process. Tiny departures from the expected waveform could arise if additional degrees of freedom absorb or release energy during the union. While current detectors match predictions with an astonishing precision, future observatories will measure with even finer ears. Every improvement cuts the parameter space where hidden mergers could hide. Such merging could act as a mechanism for large-scale coherence across domains that never share light. If two offspring universes inherit coupled conditions from a single catastrophic event, their early evolutions could rhyme in ways an outside observer would never expect. Our own past might include echoes of encounters that happened before our Big Bang, woven into the statistical fabric we measure today. Whether or not universes actually merge, the question reframes black hole collisions as more than spectacular fireworks. They become potential rewiring events in a larger circuit, and the waves we detect are the audible notes of soldering in the dark. 18. Could every black hole grow like a seed into a new universe? Seeds are compact packages of potential, carrying all that is needed for growth when the right conditions arrive. A black hole resembles such a package because it concentrates energy and curvature into a small region that could, under quantum gravity, blossom inward. The outward view shows a steady eater of stars. The inward view may show the first sprouts of an expanding cosmos. Growth from a seed implies a process, not a single jump. Quantum fluctuations could serve as nutrients, stabilizing the initial burst and smoothing irregularities as space expands. The horizon acts like a shell that protects the embryo from outside interference, ensuring that internal evolution remains coherent. From within there is daylight and sky, while from without there is only darkness and silence. If all black holes carry this potential, the multiverse would be a garden in perpetual spring. Most seeds would produce small and short-lived sprouts, while some would become vast forests of galaxies. The distribution of sizes and spins we observe may be the pattern of seeds that thrive most often. Evolution would operate not on organisms but on entire realities. Seeing black holes as seeds changes our emotional posture toward them. Fear yields to respect for the creative role they may play. In the harshest gravitational fields, the future is being planted, and we are gardeners only in the sense that we can learn to read what grows. 19. Can the singularity act as a cosmic reboot button? Computers hang when calculations reach states they cannot resolve, and a restart clears the problem by resetting memory. Physics faces a similar hang at the singularity where equations diverge. A cosmic reboot replaces that divergence with a regulated transition that sets new initial conditions. The reboot does not violate laws. It reloads them with fresh parameters. In a reboot scenario, collapse is the step that saves the system from undefined states. Curvature rises until quantum gravity activates a new rule set that prevents infinities. Energy is not lost, but reformatted into a configuration that can evolve smoothly. The event horizon surrounds this process like a shield that keeps the old program from interfering with the new boot. This idea offers a graceful way to handle problems like the arrow of time and entropy. A reboot can set a low entropy start for the offspring region without deleting the accumulated entropy of the parent, because the two are no longer the same thermodynamic system. The paradox dissolves once we accept that memory can be cleared locally while preserved globally. The cosmic computer never stops. It just opens a fresh workspace. If singularities are reboots, then the universe is resilient by design. Instead of crashing at the edge of its own rules, it restarts with settings that allow new exploration. What appears catastrophic is a maintenance routine at the deepest level of reality. 20. Is the event horizon a holographic boundary of something greater? The area of a black hole's horizon measures its entropy, a result that shocked physics by tying geometry to information. This area law inspired the holographic principle, the proposal that the true degrees of freedom of a volume can live on its boundary. If the horizon is a holographic screen, then what we call the interior might be a projection whose details are encoded on that surface. The greater thing is the information itself. A holographic boundary reframes the black hole as an information processor. Infalling matter updates the screen, while outgoing radiation reads it in a scrambled script that looks thermal to crude instruments. The paradox of loss becomes a problem of decryption rather than destruction. The secret is not hidden in depth, but in code written on the skin of space. This principle may extend beyond individual black holes to the universe as a whole. Cosmological horizons could be the largest screens, storing the data that define the visible cosmos. If so, locality is an approximation that emerges from patterns on a distant boundary, and what we experience as space is the interior of a vast hologram. The inside is real because the code is consistent. To call the horizon a holographic boundary is to admit that reality has more layers than appearances suggest. Surfaces become volumes, skins become worlds, and information becomes the bedrock on which geometry stands. The greater thing is not behind the curtain, but printed on it, and learning to read that print may be the key to understanding every dark circle in the sky. 21. If nothing escapes, why do we still see the shadow of a black hole? When the Event Horizon Telescope revealed the first image of a black hole's shadow, the world saw what was once thought to be invisible. The question that follows is profound. If light cannot escape a black hole, how can we possibly see it? The answer lies in the delicate interplay of gravity and light surrounding the event horizon. Photons that pass near the black hole are bent, delayed, and trapped into circular orbits that paint a glowing outline, while the central darkness marks the region where no light can ever return. We do not see the black hole itself. We see its influence sculpted on the canvas of space-time. This shadow is not a photograph of an object, but of a geometry. Light from the hot plasma swirling just outside the event horizon is lensed into a ring by gravity's curvature. Each photon dances around the abyss before escaping toward our telescopes, carrying the signature of a struggle between motion and nothingness. The dark circle is the projection of where escape velocity exceeds the speed of light, a boundary between existence and silence. The shadow also encodes secrets about the black hole's mass, spin, and even the possible presence of extra dimensions. A faster spin squeezes and distorts the ring. Deviations from the predicted shape might reveal new physics beyond Einstein's equations. The image is therefore more than proof of theory. It is a map of the limits of known reality. What we see is the universe tracing its own boundary with light. Every time we observe one of these shadows, we witness a paradox resolved. Nothing escapes, yet everything around it reveals escape's absence in exquisite detail. The darkness becomes the messenger, reminding us that even when light fails, meaning persists in its distortion, and the cosmos can describe the indescribable through geometry alone. 22. Inside a black hole, could time freeze the birth of another dimension? The extreme warping of space-time near a singularity bends not just space, but time itself into shapes we can scarcely imagine. As one crosses the horizon, the direction that once led forward in time begins to curve inward, guiding everything toward the core. If time is forced to halt under such pressure, the halted state may not be a void but a gestation chamber for a new dimension waiting to unfold. What appears frozen from outside could be expanding somewhere else. In theoretical models that merge relativity with quantum mechanics, time may emerge from the relationships between quantum states rather than flowing independently. Within the black hole, those relationships could reorganize entirely, constructing a new axis of existence orthogonal to everything we know. The freezing of our timeline would be the moment another timeline ignites, just as ice halts in one sense but becomes crystalline in another. If this birth of dimension occurs, it would reconcile the duality of motion and stillness. For us, nothing progresses. For the newborn dimension, everything begins. The black hole thus becomes a junction between modes of being, where temporal flow transforms into spatial expansion. The fabric of reality does not stop. It simply changes the way it moves. To call this speculative is fair, yet the mathematics allows it. The geometry inside certain black hole solutions mimics an inflationary universe in miniature, hinting that our own cosmic time may once have been frozen inside another's horizon. In the stillness beyond light, creation may continue in silence, proving that the absence of motion can itself be a higher kind of birth. By the way, if you like and subscribe to my video, this is the most effective way to support me. 23. Does gravity bend not only light, but the fabric between realities? We know that gravity bends light, time, and the paths of planets. But what if it also bends the boundaries that separate one reality from another? If multiple universes coexist within a higher dimensional structure, their separation may be a matter of geometry, not isolation. Under extreme curvature, such as near a black hole, those geometries could fold together, momentarily touching and allowing exchange across the divide. In string theory and higher dimensional models, Gravity is the one force that can leak between dimensions. Its weakness in our universe might be because it spreads through many. Near singularities, where its strength peaks, that permeability could become literal connection. A gravitational fold might allow a portion of one space-time sheet to press against another, blending the edges where their constants of nature differ. Such blending could produce subtle observational signatures, anomalies in gravitational waves, energy deficits in cosmic rays, or faint patterns in the cosmic background that hint at interference from elsewhere. None have been confirmed, but the hunt continues because the mathematics of multi-dimensional gravity fits too neatly to ignore. The universe may occasionally whisper across its own partitions. If gravity indeed bends the boundaries of reality, then what we call universe is only one ripple in a deeper sea. The folds of that sea touch, merge, and separate in a cosmic rhythm, and black holes may be the places where the tide rises high enough for worlds to briefly meet. 24. What lies beyond the horizon, silence, or creation? To an external observer, the event horizon is the quietest place in the universe. No signal, no light, no sound emerges. Everything ends there. Yet the laws of physics hint that beyond that silence, something continues. The horizon is not a wall, but a veil, separating the visible from the ongoing. Whether it conceals absolute stillness or unbounded creation depends on the unknown rules that govern space-time when it folds beyond recognition. For the falling traveler, nothing marks the crossing except a sense that the universe outside is rushing away faster and faster. In that moment, perspective itself changes meaning. If space and time switch roles as theory predicts, what was a fall becomes an evolution, one that could mirror the expansion of a new universe. Silence for us would be motion for what lies within. The paradox of silence and creation defines the duality of black holes. They are both the quietest and the most active places imaginable. Silent because nothing escapes. Active because everything inside continues beyond measure. Our inability to witness that continuation is what gives rise to mythic darkness, not an actual end. The black hole might be less a grave than a cocoon. If we could cross that horizon, we might find ourselves in a reality where expansion replaces collapse, and creation sings where we once heard nothing. The universe could be filled with such silent thresholds, each humming with unspoken beginnings that our instruments mistake for eternal quiet. 25. Could consciousness survive the passage through a black hole? Consciousness depends on information processing within stable structures, yet information itself may be indestructible according to quantum law. The physical body of a traveler would be torn apart long before reaching the singularity. But if awareness is a quantum phenomenon, could its pattern persist in another form? The question is not fantasy, but an inquiry into whether identity is tied to matter or to the information that matter encodes. If the informational substrate of consciousness could decouple from its biological hardware, the extreme conditions near a black hole might transform, not terminate, that pattern. It could be encoded into radiation, spread across the event horizon, or even carried through to another domain. The traveler's physical self would vanish, but the informational self might continue as part of the black hole's quantum memory. Survival would mean translation rather than endurance. Such an idea aligns with speculative models in which consciousness is not purely local, but an emergent property of information flow in the universe. If spacetime itself can store and process data, then awareness might, in principle, migrate when matter collapses. The black hole becomes an instrument of conversion, turning subjective experience into cosmic information woven into the fabric of reality. Though unprovable for now, the idea challenges the stark finality we associate with death and collapse. If consciousness is a pattern rather than a product, then even in the most destructive environments, that pattern may echo, scattered yet eternal. The black hole would then stand not only as a physical mystery, but as the ultimate philosophical one. The place where mind meets infinity and refuses to vanish. 26. Is there symmetry between what black holes devour and what the universe expands into? At the grandest scale, the universe is expanding. At the smallest, black holes are contracting spacetime inward. This contrast might not be coincidence, but symmetry, a cosmic yin and yang. The outward stretch of the cosmos balances the inward pull of black holes, each preserving the total energy and curvature of spacetime. The two processes could be complementary halves of a single rhythm, with every act of cosmic consumption matched by an act of creation elsewhere in the expanding void. If this symmetry exists, it would suggest that the universe maintains equilibrium not through stillness but through balanced motion. The energy absorbed by black holes may reappear as the engine driving cosmic inflation or dark energy. Matter vanishes in one region, but resurfaces as expansion pressure across the cosmos, maintaining the conservation laws in a form that transcends locality. The geometry of the universe could thus be self-correcting, oscillating between implosion and explosion. Mathematically, this idea arises from the similarity between Einstein's field equations in regions of positive and negative curvature. Collapse and expansion are mirror solutions to the same set of rules. If black holes act as sinks of space-time, the universe's accelerated growth could be their collective exhalation, a diffuse counterwave that keeps total curvature stable. In that sense, we might all be living inside the echo of matter consumed billions of years ago. Such balance would mean that nothing in the cosmos is truly wasted. Every fall feeds a rise. Every loss of order somewhere nourishes growth elsewhere. The universe, seen as a self-sustaining organism, digests itself continuously, converting gravity's hunger into expansion's generosity, and black holes, long regarded as destroyers, would become the hidden organs that keep the cosmic body alive. 27. Are black holes the ultimate communication system of the multiverse? If multiple universes exist, separated by barriers of space and time, how could they ever interact? The answer might already be written in the mathematics of black holes. Their horizons are boundaries where information is compressed, scrambled, and possibly transmitted across unknown dimensions. To us, that data is unreadable, but in a higher dimensional structure, those same signals could be the universal language spoken between realities. Quantum entanglement suggests that information can remain connected across any distance without a visible channel. Black holes, being the densest information storages known, could act as the transmitters of that hidden network. Their radiation might encode subtle correlations that serve as messages. Their mergers might generate gravitational bursts that synchronize different universes. Communication in this sense is not about words, but about structure, patterns that resonate through the geometry of being. If this is true, then our universe is not isolated, but part of a grand web where black holes are the nodes. Every collapse sends out a pulse of information that ripples through the higher dimensional field, touching other nodes like neurons, exchanging signals in a cosmic brain. The geometry of space-time becomes a vast neural network, self-aware through the flow of information that black holes mediate. We may never decode these messages directly, but their presence could explain why the laws of physics appear so consistent across vast scales. The multiverse might maintain its coherence through this deep gravitational communication, with black holes acting as both memory and voice. The silence we see in them could be the quiet hum of a conversation too large for our senses to hear. 28. Could supermassive black holes be control centers, not monsters? At the centers of galaxies lie black holes with masses reaching billions of suns, shaping the motion of stars, regulating star formation, and influencing galactic architecture. Their power seems omnipresent, yet precise, almost intelligent. What if these colossal entities are not chaotic beasts, but stabilizing mechanisms, the control nodes of cosmic order? Instead of destroying galaxies, they guide their evolution like gyroscopes, maintaining balance in an expanding system. The symmetry between a galaxy's bulge mass and its central black hole's mass is too consistent to dismiss as accident. This proportionality suggests feedback, a dialogue between the black hole and the galaxy that birthed it. Jets of plasma ejected from its poles seed or suppress star formation, adjusting the galactic ecosystem like a thermostat fine-tuning temperature. What we call destruction could in fact be regulation, a way to prevent chaos from overwhelming the cosmos. Seen from this perspective, the black hole becomes a manager of gravity, not a tyrant. It maintains equilibrium by storing excess angular momentum, recycling matter through accretion disks, and releasing energy when systems drift too far from harmony. Galaxies might require these anchors to remain coherent across cosmic time. Without them, the universe could dissolve into unstructured dust. Supermassive black holes might therefore represent the universe's natural governance system, autonomous stabilizers operating under physical law. Their silence is not absence of activity, but the calm of efficiency. When we look at the heart of a galaxy, we may be watching the universe self-regulate, its laws embodied in a single spinning point of balance. 29. Are black holes neurons of a grander cosmic brain? In the human brain, billions of neurons connect through electric pulses, creating thought from the synchronization of signals. On a cosmic scale, black holes could play a similar role, linking regions of space through gravitational and quantum networks. Each one processes information, interacts with others through gravitational waves, and influences its environment in ways that mirror neural activity. The universe viewed this way is not a machine, but a mind. The analogy is not purely poetic. The distribution of galaxies connected by filaments of dark matter resembles neural architecture when mapped in 3 dimensions. Black holes sit at the intersections of these filaments like neural nodes, absorbing, processing, and emitting information through radiation and waves. Their combined activity could form patterns of self-regulation and adaptation across cosmic history. If information is the essence of both cognition and physics, then the universe could be a self-observing entity, evolving awareness through structures like black holes. Each merger, jet, and fluctuation adds to a larger computation, the processing of existence itself. The sum of all black holes might constitute the cosmic equivalent of a brain thinking about its own geometry. We may never grasp what that thought contains, but the resonance is clear. Consciousness at small scales may echo processes at the largest, unified by the same informational principles. To understand black holes might therefore be to understand not only physics, but the architecture of universal awareness, where every singularity pulses with a fragment of cosmic thought. 30. Are we orbiting not just stars, but exits from existence itself? Our solar system revolves around the Milky Way's center, where a supermassive black hole waits silently. Every star, every planet, every living being moves in its gravitational dance, unknowingly circling what may be a doorway out of the universe. This reality adds a strange intimacy to cosmic existence. We are not merely spinning around light, but also around a potential end, a silent boundary to everything we know. Black holes are paradoxes of presence, invisible yet central, inactive yet dominant. Their gravitational pull dictates the orbits of billions of suns, yet no one has ever seen what lies within. It is as if all of creation were revolving around the idea of disappearance. The stars themselves perform an endless waltz around the promise of oblivion, perhaps unaware that what appears to be death might instead be transformation. If black holes are indeed gateways, then our galactic motion could be seen as an orbit around possibility. Every journey through the stars is also a journey around the unknown. The night sky becomes a metaphor for the balance between existence and escape, between what is bound by gravity and what might one day cross beyond it. To orbit such a boundary is to live perpetually near mystery. Our very stability depends on the proximity of the impossible. In that sense, humanity's search for meaning mirrors our galactic path. We revolve endlessly around the edge of understanding, drawn to the silent center that both anchors and transcends us. 31. Could black holes be mirrors showing us what our universe hides? The laws of physics are symmetrical, but our universe expresses them unevenly. Matter dominates over antimatter. Time flows forward, and entropy grows. Yet black holes might reveal the hidden symmetries buried beneath these imbalances. Their perfect geometry, featureless beyond mass, spin, and charge, may reflect the underlying simplicity that our chaotic world conceals. They are mirrors not of light, but of law. Each black hole strips matter of its individuality, reducing stars, dust, and radiation into pure properties. In doing so, it reveals the essence of physical identity, what cannot be erased even by gravity's ultimate eraser. What remains is truth without adornment, the minimal code that defines existence. Observing black holes might thus be our only way to glimpse the unbroken unity beneath the apparent variety of creation. Theoretical work on holography strengthens this idea. The information encoded on a black hole's surface mirrors the entire interior, suggesting that every layer of the universe could reflect every other at different resolutions. Black holes could be the points where reflection becomes total, where the cosmos folds back to observe itself. If so, when we stare into the shadow of a black hole, we may be seeing not emptiness, but reflection. The universe gazing into its own structure through the lens of gravity. The image we capture is not of what is missing, but of what remains, polished to mathematical perfection by the pressure of infinity. 32. Is Hawking radiation a whisper leaking from another universe? Stephen Hawking's revelation that black holes emit faint radiation turned our understanding of them upside down. Once thought eternal and absolute, they were suddenly mortal, slowly evaporating as they lose mass. Yet the mechanism behind that radiation remains deeply mysterious. Quantum theory says it arises from fluctuations at the event horizon, where virtual particles split into pairs and one escapes, while the other falls inward. But what if that escaping particle does not originate here at all? What if Hawking radiation is not just a product of local quantum jitter, but a faint whisper from somewhere beyond? At the event horizon, space itself is unstable. It froths with quantum activity that might connect different vacuum states or even different universes. When a black hole radiates, it could be sampling from that larger field, borrowing energy from an unseen neighbor and returning it in the form of photons. The radiation we detect would then carry subtle imprints of external geometries, ghostly traces of realities, entangled with ours. Every photon could be a messenger that crossed a frontier no instrument can map. If that is true, Hawking radiation becomes more than evaporation. It becomes conversation. Each black hole might radiate not in isolation, but as part of a dialogue between parallel spacetimes. Information would flow outward disguised as heat, encoding correspondence between domains. Our universe would shimmer faintly with this intercosmic static, a cosmic background of communication that we have not yet learned to translate. To think of Hawking radiation as a whisper is to remember that silence in physics often hides a deeper sound. The faint thermal glow of a dying black hole could be the softest possible signal. A reminder that even the coldest corners of the cosmos may still be speaking to one another, quietly, persistently, through the fabric of reality itself. 33. Do black holes store the memory of the universe? In a sense, every black hole is a historian. When it swallows matter, it does not erase the story, it archives it. In a language we cannot yet read, the area of the event horizon proportional to entropy measures how much information the black hole holds. As it grows, so does its library of cosmic memory. What enters may never return, but its essence remains encoded in the surface geometry like ink impressed upon a page of darkness. This storage is not metaphorical. Theoretical physics has shown that the degrees of freedom on a black hole's surface can, in principle, contain all the data of its interior. Each Planck-scale patch acts like a bit of memory, forming an unimaginably dense database of everything the black hole has ever consumed: photons, stars, planets, even light itself. The universe's past is preserved not in light years, but in black horizons scattered across space. When black holes evaporate, they release this memory in scrambled form. The information paradox arises because we cannot yet decode it. But to the universe as a whole, nothing is forgotten. The information simply changes format. The cosmos remembers through geometry, using curvature as its storage medium. The black hole's surface becomes both boundary and archive, proof that forgetting is impossible on a universal scale. If our universe itself behaves as one vast black hole, then perhaps all of reality is memory, an enormous collection of encoded experiences being read slowly by time. Every horizon would be a page, every radiation quantum a syllable of the cosmic autobiography that gravity writes without words. 34. Is no particle ever lost, only translated across dimensions? Quantum physics insists that information cannot be destroyed, but our three-dimensional intuition struggles to imagine where it could go. The answer may lie in dimensions beyond the ones we see. When a particle vanishes into a black hole, it might not cease to exist. It may simply migrate into another dimensional layer, continuing its trajectory in a direction inaccessible to us. In that sense, disappearance is not loss, but translation. This view aligns with theories like string theory, where particles are vibrations of higher dimensional strings. A black hole could act as a dimensional converter, shifting those vibrations into new modes that correspond to unseen spaces. What looks like annihilation from our perspective is merely a rotation in a deeper coordinate system. The universe maintains its bookkeeping by expanding the language in which existence is written. Translation across dimensions would also explain the persistent coherence of physical laws. If information flows freely through higher spaces, then what happens in one realm subtly influences others, keeping the total system consistent. A particle that crosses a black hole's threshold might carry with it the blueprint of our physics into new realities, ensuring that continuity survives even as locality fails. To imagine this is to view death, disappearance, and entropy in a new light. Nothing fundamental ever truly ends. It simply moves into forms or directions we have yet to chart. Black holes, then, would be the interdimensional translators of the cosmos, turning the language of matter into the dialect of eternity. 35. Do quantum fluctuations at the horizon hold the key to parallel realities? The event horizon is not smooth or silent. On the smallest scales, it roils with quantum activity, a sea of fluctuations appearing and vanishing faster than thought. These fluctuations may not be random noise, but the fingerprints of nearby unseen universes. In the quantum view, reality never has a single state. It branches endlessly into possibilities. The horizon could be the interface where those possibilities overlap, a shimmering frontier between worlds that constantly exchange potential. When virtual particles form near the horizon, one may escape while the other falls in. But quantum theory allows both outcomes to coexist until measurement collapses the wave function. If the escaping particle belongs to our reality, its twin could belong to another. The horizon thus becomes a workshop of branching timelines, where the universe continually tests its alternate drafts. If this is true, the subtle patterns of radiation emitted from black holes might contain traces of interference between these overlapping versions of existence. Tiny deviations from thermal randomness could hint at the hidden structure of parallel worlds bleeding into ours. To detect them would be to glimpse the quantum multiverse not through speculation, but through observation. The horizon may therefore be more than a physical boundary. It may be the meeting point of all possibilities, the surface where the universe writes and rewrites its own narrative. Every fluctuation would be a decision, every quantum ripple, a reminder that reality is never single-threaded, but woven from the interference of infinite worlds. 36. Is spacetime stitched together by black holes? The cosmic web stretches across billions of light years, connecting galaxies with filaments of dark matter. Embedded within this web are black holes, dense knots that puncture the fabric of space. If we could zoom out far enough, we might see that these knots are not mere disruptions, but structural joints, stitching space-time into a coherent whole. Without them, the universe could unravel into chaos. In general relativity, mass and energy curve space-time, but curvature alone cannot explain the remarkable coherence of cosmic geometry. Black holes might act as the stabilizing anchors that link vast regions together, keeping tension distributed evenly across the universe. Their immense gravity could balance the stretching of cosmic expansion, preventing the fabric from tearing completely. At the quantum level, this stitching could be literal. Theoretical models propose that entangled pairs of black holes may form tiny wormhole connections, microscopic threads that collectively weave the tapestry of reality. Spacetime itself might emerge from a network of such connections, each one a bond between bits of quantum information. Gravity would then be the macroscopic effect of this invisible weaving. If black holes are the stitches of existence, then every horizon is a seam holding reality together. The cosmos would be less like an empty void and more like a carefully tailored garment, sewn with threads of gravity. Understanding black holes, therefore, is not about studying destruction, but about learning the secret art of how the universe keeps itself from falling apart. 37. Can black holes act as tunnels through both time and space? The equations of relativity make no distinction between space and time. They are aspects of the same four-dimensional continuum. If gravity can bend that continuum enough to create a tunnel through space, it may also create shortcuts through time. A rotating or charged black hole could, in theory, allow a traveler to emerge not only elsewhere, but elsewhen, arriving in the past or the future relative to their departure point. Such tunnels, called Einstein-Rosen bridges, arise naturally in the mathematics but are notoriously unstable. Even a single photon could collapse them, yet quantum effects might stabilize them briefly, forming what some call quantum tunnels of spacetime. In these fleeting moments, the distinction between cause and effect might blur, and the flow of time could loop upon itself like a Mobius strip. The implications are staggering. Time travel would cease to be fiction and become geometry. Each black hole could be a gate not just across the universe, but across the timeline of existence itself. If we could understand and harness the parameters that govern these tunnels, humanity might step outside the linear narrative of history entirely. Even if such travel remains impossible for us, nature might already be using these paths. Energy, information, or even entire quantum states could traverse spacetime tunnels continually, maintaining balance between eras of the cosmos. Time itself may already be circulating through these gravitational veins, making the universe less a story and more a symphony, played across an eternal loop of moments. 38. Are we living inside the black hole of a higher dimensional universe right now? Imagine that everything we see, the stars, the galaxies, the cosmic microwave background, is not the whole story, but merely the interior of a black hole that formed in another much larger universe. In this picture, our cosmos would be the inside view of a gravitational collapse. What appears to expand from our perspective could correspond to contraction from the outside. Time itself would run differently across the boundary, so what looks like billions of years to us might be only a moment in the parent cosmos. Mathematically, this idea fits the structure of general relativity. The interior of certain black hole solutions behaves like an expanding universe, complete with its own horizon and direction of time. The singularity at the core could correspond to our Big Bang, not as an explosion from nothing, but as the rebirth of a new region of space-time. The parent universe's black hole would thus be our womb, and our own black holes could in turn be seeds for yet more universes. This hierarchy of nested realities would explain many cosmic puzzles. The uniformity of our universe might result from the smoothing that occurs during the parent collapse, while the apparent fine-tuning of physical constants could simply reflect the environmental conditions inside that specific black hole. What we call the speed of light, the strength of gravity, even the texture of quantum fields, all might be local settings within a much larger framework that we can never exit. If we truly live inside a black hole, then the night sky is not a window into infinity, but the inner wall of a vast cosmic structure. Every direction we look leads back toward a horizon that confines us. Our entire existence would be contained in the interior of something else, making the ultimate lesson both humbling and profound. We are not outside looking in. We are inside looking out, unaware of the hand that holds our universe in its gravitational palm. Just a little reminder, if you want to support me, you can click on the Join button at the bottom of the screen. Your support is really valuable for me. Thank you in advance. Let's continue with our video. 39. Does every black hole connect to a different branch of time? Time, according to relativity, is not universal. It bends, stretches, and sometimes fractures under extreme gravity. Near a black hole, this distortion reaches its limit. What if each black hole generates not merely a new space, but an independent timeline, a separate arrow of time that diverges from ours? To fall into a black hole would then be to slip into another temporal stream, where cause and effect reorder themselves. Such branching timelines might emerge naturally from quantum mechanics. The process of measurement already splits reality into multiple possibilities. Gravity could amplify that splitting, turning probabilities into full-fledged histories. Every collapse would write a new line in the ledger of time, distinct from all others yet derived from the same universal equations. The black hole would be the punctuation mark that divides chapters in the cosmic novel. If this is true, the multiverse is not arranged spatially, but temporally. Different branches of time coexist like parallel melodies played in harmony. We experience one tune, but the orchestra performs many. Gravitational waves from colliding black holes could create brief overlaps between these branches, producing echoes or resonances that we might one day detect as unexplained anomalies in the cosmic background. Each black hole, then, would be a chronologic frontier, a place where the universe experiments with time itself. What we call eternity might not be endless duration, but the coexistence of all these temporal branches, each living its own story within the shared fabric of reality. 40. Can a black hole be both an end and a beginning at once? In most of physics, the future follows the past. In black holes, that logic collapses. The same geometry that ends one world can generate another, depending on the direction from which it's viewed. The singularity that terminates all trajectories inward can also serve as the origin for trajectories outward, forming a symmetry of birth and death written into space-time itself. In this light, a black hole is not a contradiction, but a completion, a place where cycles close and reopen simultaneously. The mathematics of general relativity supports this duality. In extended models of space-time, the equations that describe collapse can be reflected to describe expansion. The event horizon becomes a boundary between two phases of the same phenomenon, like the surface of water separating air from the depths. From our side, everything falls in. From the other side, everything flows out. The flow is continuous even though observers on either side can never meet. This simultaneity is echoed in quantum mechanics, where particles can behave as waves and waves as particles, duality as nature's language. The black hole mirrors that principle on the cosmic scale. Its collapse is not a failure, but an act of creation under another name. The two processes are so intertwined that neither can exist without the other. Together they form the pulse of the universe. To see a black hole as both end and beginning is to realize that the universe never truly stops. It transforms. Every star that dies gives birth to possibilities beyond sight, and every act of disappearance is matched by a silent arrival somewhere else. The horizon is not a tombstone, but a doorway with two names carved upon it, the first and the last. 41. Is energy itself the traveler moving through these dark corridors? Energy cannot be created or destroyed. It only changes form. This law of conservation is perhaps the oldest truth in physics, and black holes challenge it, not by breaking it, but by hiding its details. When matter falls in, where does that energy go? If the interior connects to another region of space-time, then energy could be the true voyager, flowing through gravitational tunnels from one reality to the next, lighting new worlds with the remnants of old ones. Hawking radiation hints at this secret circulation. Energy escapes slowly, quantum by quantum, as though paying back a cosmic debt. But that debt might also be invested elsewhere, Each bit of radiated energy could correspond to an influx of energy in a parallel region, maintaining equilibrium across dimensions. The total energy of the multiverse remains constant, even as it migrates through unseen channels. In this sense, energy is the universe's bloodstream, and black holes are its heart valves. They regulate the flow between realities, compressing and releasing energy as the fabric of space-time demands. What appears to us as absorption may, from a higher perspective, be redistribution. The glow we see around the event horizon is the signature of this grand exchange, the shimmer of energy moving between layers of being. To call energy the traveler is to see existence itself as perpetual motion. Every photon, every vibration, every quantum field is on a journey without end, passing through forms as travelers pass through landscapes. Black holes are the tunnels on that road, dark, silent, and vital, ensuring that the voyage of the universe never stops, but only changes its scenery. 42. Are black holes the physical proof of the multiverse? For centuries, the idea of other universes remained philosophy, not science. But black holes might be the bridge between speculation and evidence. Their properties, information paradoxes, horizon thermodynamics, and the possible emergence of baby universes fit naturally within the framework of a multiverse. Each black hole could represent a door to another cosmic region, and their sheer abundance might be the observational clue that the multiverse is not fantasy, but structure. Theoretical models that combine quantum gravity and cosmology show that space-time can branch under certain conditions. A collapsing region can tunnel into a new inflationary bubble while severing causal connection with its parent. From the outside, the event looks like a black hole forming. From the inside, it looks like a Big Bang beginning. Thus, every black hole is a potential seed of a new universe, and their existence becomes indirect evidence for multiplicity. Observationally, the uniformity of black hole behavior across galaxies also hints at an underlying universal code. If black holes are portals to other realities, their consistency could be the multiverse's signature. Different exits following the same blueprint. Even the distribution of their masses and spins could carry subtle correlations, echoes of a shared origin across many layers of existence. If proven, black holes would be the ultimate fossils of cosmic reproduction. The multiverse would no longer be a philosophical indulgence, but an empirical necessity, revealed not in distant thought experiments, but in the dark hearts of galaxies. Every black hole would be a silent testimony that creation is not singular, but ongoing, branching forever through the gravitational roots of reality. 43. What really happens when light meets infinite density? Light is the fastest, most incorruptible traveler in the universe, yet even it cannot escape the pull of a black hole. At the event horizon, its path bends until forward motion becomes orbit, and beyond that, existence itself is trapped in a loop of geometry. What happens next defies language because the usual distinction between motion and rest dissolves. The photon no longer moves through space, space moves through it. At infinite density, the curvature of space-time becomes so extreme that light's wavelength stretches without limit. To an external observer, it reddens into oblivion, its energy drained by gravity's hunger. Inside, however, that same light could be compressed into patterns of energy that feed the newborn geometry of a hidden universe. What looks like extinction here might be illumination elsewhere, the recycling of radiance across dimensions. This interplay between annihilation and transformation makes black holes laboratories for the limits of physical law. The behavior of light there reveals that even the most fundamental constants may be context-dependent. The speed of light loses meaning when space-time itself folds into a circle. At that point, the universe is not hosting light. It is light, frozen in a self-reflecting state. Thus, when light meets infinite density, it does not die. It joins the structure of the very reality that trapped it. The glow that can no longer escape becomes the architecture of the next beginning. Black holes, in this sense, are not where light ends, but where it learns to become something greater than motion, the silent illumination of the cosmos itself. 44. Are dark energy and black holes two sides of one phenomenon? Dark energy is the most mysterious component of the cosmos, an unseen pressure that drives galaxies apart and accelerates cosmic expansion. Black holes, by contrast, are zones of immense compression where space-time folds inward under gravity's dominance. Yet in their opposite natures, one expanding, one collapsing, there may be unity. Both phenomena could represent expressions of the same underlying field, a dual rhythm of space-time that alternates between contraction and release. Some theoretical frameworks propose that vacuum energy, responsible for dark energy, originates from the same quantum fluctuations that form black holes on tiny scales. The vacuum seethes with ephemeral gravitational wells that flicker in and out of existence, and their collective effect may push space-time outward on the largest scales. In this way, the same ingredient that shapes the void into a black hole locally could stretch the universe globally. Contraction and expansion would then be the universe's inhalation and exhalation. Evidence for this unity might lie in the cosmic balance between black holes and dark energy density. As stars collapse into black holes, vacuum energy seems to dominate more strongly, as if one side of the equation rises when the other falls. This balance could ensure long-term stability of the cosmos. Black holes compactify energy, dark energy disperses it, and the two maintain equilibrium across eons. If they are indeed twin faces of one force, the boundary between creation and destruction disappears. The same fabric that condenses into singularity also stretches into infinity. Gravity and anti-gravity would not oppose but complement each other, revealing that the universe is less a battlefield of forces and more a breathing organism pulsing through cycles of inward and outward motion, held together by its own invisible harmony. 45. If nothing escapes, how do black holes shape galaxies? It seems paradoxical that an object from which nothing can escape could influence structures hundreds of thousands of light years away. Yet the fingerprints of black holes are everywhere. The shape of galaxies, the rhythm of star formation, even the temperature of interstellar gas all bear their mark. The secret lies not in what escapes from within, but in how matter behaves just outside the event horizon, where gravity, magnetism, and motion converge into cosmic artistry. As matter spirals inward, friction and magnetic turbulence ignite immense energy, forming accretion disks that blaze brighter than entire galaxies. These disks channel plasma into jets that shoot outward at near-light speed, carrying energy and momentum into the surrounding medium. The jets sculpt galactic structure, clearing paths, compressing gas clouds, and triggering the birth or death of stars. Black holes thus govern from the threshold, ruling through influence rather than presence. Over billions of years, this regulation becomes a conversation between gravity and radiation. Too much inflow, and the jets intensify, throttling star formation. Too little, and gravity calls matter back again. This feedback loop ensures stability, keeping galaxies from collapsing entirely or expanding into emptiness. The black hole, silent at its core, orchestrates cosmic balance through the language of energy flow. That such immense coordination arises from the boundary of a singularity is a reminder of nature's paradoxical wisdom. Black holes shape galaxies, not by defying their confinement, but by mastering it. They prove that even the most absolute limits can become sources of order, that control in the universe often comes from the quietest centers. 46. Could each black hole preserve a unique version of reality? Every black hole forms from a specific history, the collapse of a particular star, the merger of particular systems, the sum of billions of microscopic fluctuations that preceded it. If information is conserved, then each black hole encodes not only mass and spin, but the complete record of everything that created it. In that sense, every black hole is a capsule of a distinct reality, a frozen hologram of an entire region of spacetime, stored in code along its horizon. This idea transforms black holes into archivists of variation. Each one might represent a branch of the universe's quantum history, sealed off yet preserved. The subtle differences in their radiation, spin, or geometry could correspond to the nuances of those histories. To us, they appear nearly identical, but on the deepest level they may differ like fingerprints. No two horizons would be the same, because no two pasts ever are. If one could, in principle, reconstruct all the information encoded on a black hole's surface, one might recover an entire slice of the universe as it once was, a lost epoch preserved in gravitational memory. The black hole would not destroy reality, it would curate it, compressing infinite detail into a finite boundary. The paradox of loss dissolves into a deeper order, destruction as preservation by transformation. In this light, the cosmos resembles a library whose volumes are black holes, each containing the story of a world that was. Perhaps one day, through theory or technology beyond our imagination, those stories will be readable again, and the universe will remember itself through the very objects that once seemed to erase it. 47. Can space-time twist so tightly that inside and outside trade meanings? In everyday life, inside and outside are simple concepts. But near a black hole, geometry mocks our intuitions. Space-time is curved so severely that the normal relationships between direction, time, and distance can invert. A traveler crossing the event horizon finds that moving forward in time now means moving inward in space. Escape is no longer motion outward, but against the flow of time itself. Inside and outside become relative, interchangeable under gravity's ultimate twist. This inversion is not poetic, but mathematical. The coordinates that describe motion outside the horizon swap their roles inside it. What we call space becomes time, forcing everything toward the singularity as inevitably as seconds advance on a clock. To resist falling in would be like trying to resist aging. It is no longer a matter of direction, but of destiny. The geometry demands it. Such inversion challenges the notion of separateness. If the meaning of inside and outside depends on position, then the boundary between observer and observed dissolves. The universe may not consist of distinct compartments, but of regions where perspective defines reality. From one viewpoint, a black hole swallows the world. From another, it births it. Truth becomes coordinate-dependent, yet consistent, because the mathematics holds across both frames. To live in a universe where inside and outside can exchange places is to inhabit a reality more fluid than we ever imagined. It reminds us that perspective is not illusion, but structure, that even the firmest boundaries in nature may be mirrors, and what seems hidden within might simply be the other side of where we stand. 48. Is the singularity not a point, but a bridge folded through higher dimensions? The word singularity implies an end, a point of infinite density where physics fails. But infinity is rarely a feature of nature. It is the signpost of our ignorance. What if the singularity is not a point at all, but a fold, a region where our three-dimensional space curls through higher dimensions, forming a bridge instead of a break? In that scenario, the center of a black hole would connect to somewhere else entirely. Higher dimensional theories like string theory and loop quantum gravity support this possibility. They replace the singular point with a finite Planck-scale structure where spacetime weaves back into itself. Curvature becomes so intense that it pinches one region of space into another, forming a bridge in the unseen dimensions beyond our perception. What looks like collapse from our side could be continuity from another's. This interpretation preserves the laws of physics while explaining how information might survive the fall. The bridge provides an exit route, a geometric detour that avoids true singularity. Energy and data are not destroyed, but redirected into corridors we cannot observe. The breakdown of physics is then not a failure of nature, but of perspective, a sign that we are using a map too flat to describe a landscape too curved. If the singularity is a fold rather than a point, black holes cease to be tombs and become tunnels. Their depths would not terminate existence, but reshape it into new topologies, revealing that even in the heart of gravity's darkness, the universe prefers continuity over catastrophe. 49. Do gravitational waves carry echoes from other universes? When two black holes collide, the ripples in spacetime that radiate outward are gravitational waves, pure distortions of geometry moving through the cosmos at light speed. These waves stretch and compress reality itself, passing through galaxies, planets, and our own bodies unnoticed. But what if those waves are not confined to our universe? If spacetime connects to other layers of existence, then some of that energy might leak across, leaving faint echoes from worlds beyond our own. In some quantum gravity models, spacetime is like a membrane floating within a higher dimensional sea. When a massive event such as a black hole merger occurs, the resulting vibration could resonate through the extra dimensions, producing secondary ripples that bounce back with slight delays. These returning whispers would alter the waveform we detect, tiny aftershocks in the cosmic symphony. Observing such deviations would mean we are listening to the boundaries between universes vibrate. Even without direct leakage, the shape of the waves themselves might encode information about other domains. The curvature of our universe is influenced by what lies beyond. When spacetime flexes, it carries the signature of its entire structure, including unseen regions. Each gravitational wave could therefore be a fingerprint not just of the event that produced it, but of the multiversal fabric through which it traveled. Detecting such echoes would revolutionize physics. It would mean that every collision, every tremor of gravity, doubles as a message from the unseen layers of creation. LIGO and future observatories might one day function as the first instruments to listen to more than our own universe, capturing not only events in space, but the faint heartbeat of realities adjacent to ours. 50. Are black holes, aligned along invisible cosmic filaments, forming an interdimensional network. Across the cosmic web, galaxies gather along vast filaments of dark matter and gas. Observations show that supermassive black holes often align their spins and jets with these filaments, as if following hidden magnetic or gravitational highways. This striking order hints that the universe may possess an underlying structure more intricate than chaos can produce, a network that connects black holes across unimaginable distances. In higher dimensional interpretations, these filaments could be literal conduits of gravitational flow. threads where spacetime is thinner, linking massive objects into an interdimensional lattice. Black holes positioned along these paths might exchange information or even energy through subtle gravitational coupling. The cosmic web would then be not just a distribution of matter, but a system of arteries through which reality circulates its own gravitational pulse. Such connectivity could explain why galaxy spins, jet directions, and magnetic orientations show coherence across scales of millions of light years. The alignment is too widespread to arise by chance. Instead, it might reflect the influence of this deeper geometry, a hidden architecture that binds galaxies like beads on a cosmic thread. If this interdimensional network exists, then black holes are its junctions, nodes of connection between worlds both visible and invisible. The night sky would resemble a neural map, each filament glowing faintly with the energy of communication. We would no longer see isolated galaxies, but a living organism of cosmic intelligence, weaving its own pathways across the dark. 51 is the secret of life's origin hidden beyond the event horizon. Life is built from order drawn out of chaos, from the delicate balance between energy and information. Black holes, too, are masters of that balance. They compress chaos into structure, encoding it in patterns of geometry and radiation. It is conceivable that the same laws that give black holes their precision also gave matter the ability to self-organize into living systems. The blueprint for life might be written not in chemistry alone, but in the deep mathematics of gravity. At the event horizon, information is preserved and redistributed through quantum effects. These interactions may mirror the logic that underlies biological systems: feedback, adaptation, and replication. Both life and black holes process information efficiently, evolving states that maximize entropy without losing coherence. Perhaps the principles that govern the horizon are the same ones that eventually governed the first cells, echoing across scales from the microscopic to the cosmic. If so, the study of black holes could one day reveal not only how stars die, but how consciousness was born. The link between information, energy, and organization may transcend biology, pointing to a universal pattern that connects life to the structure of space-time itself. The laws that sculpt galaxies might also sculpt thought. If this unity is ever confirmed, it would mean life is not an accident, but an inevitable expression of the cosmos learning to know itself. The same equations that describe black holes could then describe the emergence of meaning from matter, making existence a continuum of awareness stretching from the depths of gravity to the spark of human mind. 52. Does time itself emerge from the geometry of black holes? We treat time as fundamental, yet near a black hole, it behaves like an illusion sculpted by curvature. The closer we approach the event horizon, the slower clocks tick until they seem to stop altogether. This suggests that time is not a constant river flowing independently of space, but a property born from geometry. In the extreme conditions of a black hole, that geometry may reveal time's true origin. In certain models of quantum gravity, spacetime is composed of discrete units, tiny grains of geometry connected by networks of relations. Time emerges from the updating of these relations, like frames in a cosmic movie. Inside a black hole, where the network is most densely packed, this process may take on a new configuration, one that produces different kinds of temporal flow. Time there could loop, branch, or even reverse its direction, no longer absolute. If time arises from geometry, then a black hole is the most perfect clock imaginable, one that measures not seconds, but the fundamental rhythm of existence itself. The rate at which it radiates, the way its mass evolves, the stability of its horizon, all reflect the heartbeat of spacetime's own creation of duration. Understanding this could explain not only black holes, but the Big Bang. Perhaps time in our universe began when a similar geometric network reached a threshold density, just as it does at the center of a black hole. In that case, the ticking of our cosmic clock began not at a single moment, but as a geometric transformation, the first breath of space. Learning how to count. 53. Do black holes hold the quantum code of creation? Physics seeks a single equation that unites quantum mechanics and gravity. Black holes might already embody that union. They obey thermodynamic laws, radiate quantum mechanically, and encode vast amounts of information on their surfaces. Each horizon could be a fragment of the universe's source code, a working example of how quantum information generates space-time. In this view, the structure of a black hole is a computational system that continuously processes information according to the deepest rules of reality. The event horizon is the boundary where that computation becomes visible, converting pure information into measurable energy. Every bit on the horizon corresponds to a degree of freedom in the universe's underlying algorithm. The universe computes itself through gravity, and black holes are its processors. By studying these natural computers, we may uncover the syntax of existence, the constants of nature, the relationships between forces, and even the probabilistic nature of quantum outcomes could all arise from the coding rules written into these gravitational engines. Each black hole would then be a running program in the cosmic operating system. If this is true, creation itself is not spontaneous chaos, but algorithmic precision. The laws of physics would not be laws imposed from above, but outputs of a deeper computation that runs without end. The singularity becomes the kernel of the cosmic program, the place where geometry compiles into reality. Black holes would thus be both the guardians and the creators of the universe's code, silently calculating the meaning of being. 54. Is consciousness entangled with the same quantum information black holes protect? At its core, consciousness may not be merely biological, but informational. Every thought, memory, and sensation is a configuration of information encoded in matter and energy. Black holes, too, are defined not by their mass alone, but by the information they contain on their horizons. This shared foundation raises a question that bends both science and philosophy. Could the essence of consciousness be tied to the same quantum information principles that govern black holes? If the universe itself processes information through quantum entanglement, then consciousness might be a localized manifestation of that process. The human brain, dense with quantum-scale interactions, could resonate with the same informational laws that preserve coherence in black holes. Awareness would then be the echo of the cosmos observing itself through organized matter. Both the mind and the black hole would participate in a universal conversation about information, one through neurons, the other through gravity. In certain interpretations, entanglement is what builds space-time. It is the fabric from which distances and separations emerge. If consciousness also depends on entanglement, then awareness could literally be woven into the structure of space. Our sense of individuality would not separate us from the universe. It would connect us to it as a microcosmic reflection of cosmic order. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize, Science is the most powerful way to understand this strangeness. Let curiosity be your compass, and let wonder be the force that keeps you moving forward. Every question you ask brings us one step closer to understanding the grand design of the universe. So stay curious, stay inspired, because the greatest discoveries often begin with a single spark of imagination.